Hence, the job fair is coming tomorrow. So tune in at 6:30 on Zoom if you're wanting to get a job. Even if you don't think you're ready to get a job yet, you might want to tune in just to listen to the employers describe what skills they're looking for. Then in conjunction with Pacific Hackers, we're having a social engineering talk coming on the 20th, and there will be food here. So register in advance if you want to come physically and get some of the food. You can also attend remotely. And on Saturday, on February 22, a couple of weeks away, we're going to have another Hacking Club event at 10. And you can come physically to it in Multi-Use Building 255 on Saturday, or you can tune in remotely by Zoom. So all these things are good and worth extra credit. And let's get into Chapter 4, which is the chapter we're up to for cryptography. So we'll talk about block ciphers, and the main one we're going to use is AES, the recommended one by the government, which seems to be perfectly fine and everybody's trusting it. And then we'll talk about what can go wrong. There are a few things that can go wrong with it. So the U.S. first defined a standard called DES, the Data Encryption Standard. This, unfortunately, was an example of government corruption. The NSA Lucifer proposed. IBM proposed something called Lucifer that was a 128-bit cipher, which would have been secure, and the NSA lowered it to 56 bits so they could crack into encryption routines. And this is what they do repeatedly, and what the UK is now doing again. Law enforcement agencies don't want anybody to be able to hide anything from them, so they have programs to try to trick people into using insecure encryption so they can get in. And the plan is to have, the National Security Agency wants is something they call NOBUS, nobody but us. They want to have a secret backdoor into it that nobody can use except them. But all attempts to do that have typically failed. And what they've done is weaken it so bad guys can get in too. That's what tends to happen. Anyway, there are a lot of block ciphers, as you see, over the last several decades. Various governments have made it. And so a block cipher is you have an encryption algorithm, you have a key, you have a block of plain text, and you create a block of ciphertext by encrypting the key and the plain text together. And then you decrypt it, if you have the key, by decrypting based on the key and the block of ciphertext. So you must somehow distribute the key to the other person you're talking to. They have to hold the secret key, and that is the intrinsic difficult part of this. You apparently have some trusted channel to deliver the key. So if you do, why didn't you just deliver your message by that trusted channel? What do you need encryption for anyway? That's the problem. But if you think about, if you're somehow like all the people are in one room, or I'm the tech support at a company, and I'm able to put the key on your computer, and then when you carry it away, the key just goes with you on the computer. You can imagine ways where this works. This is the classic kind of encryption, but it does have a key distribution issue. Somehow you have to have a secure way of distributing the key, and the person at the other end has to not lose or copy the key. If they give it to another party, then they can read all the mail, and you have no way to know that happened. So anyway, here's the security goals. The block cipher should be a pseudo-random permutation, so the attacker cannot compute a valid output without the key. They should be unable to find patterns in the data, in the relation between input and output. It should appear to just be random bits. That otherwise there'd be patterns, and they could use those patterns typically to deduce something about the key. So the block size for DES was 64 bits, 8 bytes. In AES, this was expanded to 128 bits, or 8 bytes. And this was chosen to fit into CPUs to make it fast. Block sizes below 64 are vulnerable to a codebook attack. The codebook attack is really simple. If you have a small block size, then you can just calculate, encrypt every possible plain text and place in a codebook. So if your block size is 32 bits, I can encrypt, I can make a block size of 4 billion, encrypting every possible plain text. So I can, and now the part is here, I don't see how you do it without the key. You don't know the key. Encrypt every possible plain text, place in the codebook, and then look up blocks of ciphertext. It still seems like it would take a long time. But anyway, I'm actually no longer understanding this attack. I'm going to have to go back and read the book and understand. I don't see how you get away from having to try all possible keys here. But the fact is, there is an attack against DES that came out a few years ago. I just learned about a few days ago, where in fact they attack the block size. It turns out that even if you make the key larger, if the block size is small, it can still be cracked by trying all possible block sizes. So all possible blocks of data. And I'll have to come back to this next time because I no longer exactly understand how this would work. It seems to me like you'd still need to have one of these for all quizzes. People are asking, how do you access the quiz platform? You go to samsclass.info, and then you click on the name of the class, which is CNIT 141, and then you'll find a quizzes section here that connects you to the server. And I can help you do that at 7:30 if you're stuck. All right, anyway, so to construct a block cipher, there's two techniques, substitution permutation and a phi-stel network, which is what DES uses. So you have typically have a round of calculation, which scrambles the data using the key, and then you might have 3 rounds where you encrypt it with round 1, then you have another round and another round, and then you'll have an inverse round function. You invert those rounds in opposite order. That's how the decryption algorithm works. So in this case, you often do this. All the rounds use the same algorithm, but they use a different round key, and you somehow calculate the round keys from the main key. Oh, don't worry about dumb question. That's fine. I'm here to answer any question that comes up. All right. So now, suppose you had 3 round keys, and all the keys were identical. Then, if I was able to find ciphertext with this property, if I can find plain text blocks where the first round turns this block into that block, and then I can feed that in as plain text, then I'll have this kind of situation. I could then help deduce the key from here. That's what will happen. The fact that I can break it into rounds, and the rounds are all identical, and I can slide them and compare them this way, means I can basically try to crack just one round, forward or reverse at a time. And again, I'm not remembering exactly the details here, but we are going to see one ahead that I can explain better. The meet in the middle attack, and this looks like a very similar attack. If you can somehow take the encryption process and break it up into chunks and attack just a small piece of it, then of course it gets much easier. And that's what this will do. So the solution to that is to make all the round keys different. So you cannot slide it over by one and have the same thing. If the round keys are all different, then there's no way to take a part of this encryption process and relate it to a part of another encryption process. That's the idea. So what you do in key schedule, you calculate all the round keys from the main key. And in AES, if you can get any of the round keys, you can calculate the master key from that. And therefore, if you can somehow get the round key from doing something like measuring the radio emitted or the power consumed by the processor, then that cracks it. And so that's an issue about AES. AES is vulnerable to side channel attacks. And as far as I know, every crypto system in the world is. If you can measure what the processor is doing bit by bit in the hardware, then it's very likely that you'll be able to deduce things about the key. Now, there are solutions. You can get algorithms that are constant time, for example, that always go through the same steps for every value of the key, and that helps protect you from this. And as we'll see, AES is typically done these days by hard-coded algorithms built in the processor from the start, which make it very difficult for a side channel attack to work. All right, so there's 2 things you want. You want confusion and diffusion. Confusion means that each ciphertext bit depends on several key bits. And diffusion means that if you change a bit of the plain text, it changes many bits in the ciphertext. Now, if you think about the Caesar cipher that we talked about before, where you take each letter and move it forward a bit, it doesn't have diffusion. If I change the first letter, in the plain text, it only changes the first letter in the ciphertext. So if I have a series of letters that are all the same, all the ciphertext will be the same. So that's a pattern being preserved, and that's bad. You can use that to break it. So the Caesar cipher lacks diffusion. All right. And the phi-stel schemes are what DES uses. You break the plain text into 2 halves, then you encrypt 1 half, and use an encryption routine here, and then you XOR them together and move them over here, then move that block over here. So you only encrypt half the data in each round, but then you flip it and encrypt the other half of the data, and just do 16 rounds of this. This is how, that's called a phi-stel scheme, and that's how DES worked. So let's try some Cahoots here. All right. Not letting me grab the thing. There we go. Now, don't worry about asking dumb questions. stuck on something, let me help you. People are here because they don't know what to do, so you don't have to apologize for not knowing things. Looks like we got everybody that's coming. All right, so what kind of rounds are used in AES? Uses that substitution permutation rounds. All right, and we'll go into that in much more detail in the next section. All right, so what attack can crack a cipher with a small block size? The codebook attack, which I didn't explain very well here, but it is true it's an attack that cracks things with small block sizes. So block sizes should really be larger than 64 bits now. All right, so what attack cracks ciphers with fixed round keys? That's the slide attack, where you move it over by one round and some of the operations are being repeated, and now you know a value created after just one round, and you can attack one round separately. That's the idea. All right, what type of rounds encrypt only half the plain text? That was the Feistel algorithm used by DES. Get back to the slides. Okay, so AES, the main one that matters, the one we're all using all the time. Now, DES had a 56-bit key, which is really not long enough. In fact, in 1997, using a cluster of many servers, they were able to actually try all 2 to the 56 keys. So if you can perform a brute force attack, then that system is dead, dead, dead. I mean, there's no way to defeat that. A brute force attack, we talked about this last time, the best you can possibly accomplish with any cryptographic system is to force you to use a brute force attack. If you actually have enough power to do a brute force attack, this will never work. So they created triple DES in order to be a transition scheme you could use to make DES stronger. But while people could move to triple DES right away with just a software change on hardware design for DES was the idea, but they really wanted something better, and AES was approved as the new standard in 2000. And so there's an animation of this. Let's take a look at that. Right, it's called the Rinjail cipher. I think that's the name of the cryptographer that invented it. And so you have plain text coming in, the encryption, and then the ciphertext coming out. So in it's got a state and a cipher key in hex. And so you take those and feed them in. The encryption process goes here. You add a round key. Then you do these 4 steps for 10 rounds, perhaps 9 rounds. Yeah, and then you do 3 more steps down there. That's how it works. And here's the 4 transformations that are done. You substitute bytes. So you take the bytes and just look them up, taking the first digit for the column and the second digit for the row, just transform them with this box called an S box that's just full of constant values, chosen to scramble the data. Then you shift the rows over by one, so if there were any vertical stripes, this will smear them out. And then you mix columns with matrix multiplication, so that if there were any horizontal stripes, this would mix them out. And then you add a round key, which is created without some schedule. So the point of this is these transformations are all completely deterministic, but what they do is scramble the plain text. It's like you're cutting food and you want to make hash. You cut the potatoes this way, you cut them that way, you roll them over, cut them again, mince them. You're just scrambling the data, so all the patterns in the input are just getting scrambled in a way that the output is just going to show no sign of the patterns in the input after all these rounds. And yet all these calculations are fast and easy for a processor to do. They're designed to be easy for modern processors to do it, so it'll run fast. And that's the game. And now all you need is a key schedule, which determines how you make all these round keys out of the master key. And as you can see, you do that with substitution, matrix, and so on, and some XOR operations and such. So I'm not planning to worry about all the details, but you see all the fundamental operations are very simple. They're either looking up something in a little grid of a box, or doing something simple like XOR, or just rotating the bytes around. These are all really simple little mathematical operations, but the end result in practice is it really does scramble the plain text so nobody can get in from the ciphertext. And people have, of course, been trying for a long time. As far as anybody knows, it's unbreakable. If you encrypt with AES, nobody is getting in there without the key. So they're going to have to steal the key somewhere, or they're going to have to steal the data someplace where it's not encrypted. Like I mentioned before, encryption can't solve all your problems. All encryption can do is force your attacker to steal the key some other way. Encryption stops a certain attack, and the attack this stops is the attack where they have access to the ciphertext, but they don't have the key. Like somebody on the internet seeing data going by without being at either end to get the key. So there's the internal state, viewed as an array of 4 by 4 bytes. And here's those steps. You add the round key, then you substitute bytes, shift rows, mix columns, and add a round key. So you've mixed the rows in case there's some kind of pattern that way, mixed the columns in case there's a pattern the other way, added a round key, and then you do that a bunch of times. All right. So that's the game. You use a different key every time so you're not vulnerable to slide attacks. You add the round key to make sure the key is involved in each cycle. That means the key matters. You have nonlinear operations with that substitution table, so you can't use, derivatives and mathematical operations depending on a small difference. If you shift rows, then one column wouldn't affect another column, and then you could attack the columns one by one without having to attack all the columns at once, and the same with the mixed columns. That's the point. There's no way to focus on part of it and attack just that part of it. You have to crack the whole thing, which is what you want, which means you're going to have to do a brute force attack trying all possible keys, which is the best you can ever achieve in a cryptographic system. So it's pretty easy to do in Python 3, and we'll be doing it in the project, so I don't think I'll bother you in live. I just point out it's a standard routine. There's standard libraries to input. Now you do have to have a 16-byte key. So I just put in 4 zeros, 4 ones, 4 twos, and 4 threes, which is of course not a very secure key, but it will work. And then you make a new AES object, and I'm choosing the original mode called the electronic code book, which we're going to talk more about in a few minutes, where you encrypt each block separately and independently. Here's my block, which is chosen to be 16 characters long. The input must be a multiple of 16 characters, and the output's going to be a multiple of 16 characters. So when you encrypt it, it's going to turn into this, which is 16 bytes, therefore 32 characters of hexadecimal. Just a random-looking junk. And you can decrypt it. If you have the key, you can decrypt it back to the original data. That's the idea. So to implement it, if you implement each step as a separate function, it'll be slow, but it'll work. If you use table-based implementations, that's better. And putting it in native instructions is even faster, where you build it into the processor at the microscopic level. So the processor has functions just to do AES, and all modern processors for general-purpose computers do have that for this reason. So AES is really fast. So OpenSSL is table-based. It combines the operations into something like this: shift this to the right, shift it to the right, different amounts, and then look up things in tables. You combine several steps this way, with pre-computed tables. That's just a faster way to do the operations. And so the time required for encryption would depend on the key in most implementations in software, and that's a problem. Then you can just feed in a key, for example, that's all zeros, and that will take a different amount of time than a key that's all ones, and so on. And from that, you can leak it out. With any efficient coding, one way is to use slow code that wastes time to make sure that you go through steps even when you don't have to make it a constant time algorithm. But the better solution relies on hardware. There are native instructions in the processor that are designed to flow through the transistors in a way to calculate it automatically with just one machine language instruction, and this is much safer, and it makes it much faster, and I think the time is also constant. So AES is considered very good. It was designed to resist all the cryptoanalytic attacks known at that time. The science of cryptology moves forward all the time, and people develop new ways to crack ciphers, and it was, of course, designed to resist all the known techniques at that time. Of course, somebody may find a weakness and get in, but as far as anybody knows, nothing significant has been found to break into AES 128, except the theoretical attack of quantum computers, which are not possible now, but if the quantum hardware gets much better, then they would be able to crack AES 128, but not AES 256. Now, the modes of operation introduce another problem. This is true of all block ciphers. Your block cipher means you have to feed in plain text blocks and encrypt them and get ciphertext blocks. Well, what if electronic codebook mode is also called textbook mode. This is what most people do who take a cryptography class like this or a math class. They don't think about the problem we're going to see here. Each block is just encrypted one by one. But what if your data has identical input? Like if you have network traffic. There's a lot of ART packets, and they're all the same. If you have a Microsoft Word document, there's regions of it that are all 0. If you have an image, there are regions of it that are all the same color. So you might have a plain text block here that is exactly identical to this plain text block. And if you do, the ciphertext will be exactly the same in this mode. That's not good. So here I say dead men tell no, dead men tell no. I have two 16-byte blocks that are the same. So when I encrypt it, I get 66cc, blah, blah, blah. And over here, I get 66cc, again, 2a. The second block of text encrypts to just the same output as ciphertext. So I can't read it, but I can tell that these two blocks are the same. And therefore, the Staples Android app did this. I found this out when doing a security audit by just giving it a password that was 32 A's. And it was storing an encrypted version of the password, and I found it here and reversed it, and you see there's a block of 16 bytes and an identical block of 16 bytes for the next bit of it. So they were using electronic codebook mode, which is not good. And this is in the project. This is a famous one. If you take a bitmap image, this region, that's all a constant color, the color will change. This gray will turn to green, but every future block will be the same, so you can still see the penguin. This is not what you want out of encryption. The idea of encryption was to hide the information contained in the input data, but it didn't hide the information. You can still see what the image was. So that's a serious failure of this mode. It doesn't remove all the patterns in the input. Now what you want is you want it to do this. This is what encryption should do. You encrypt it, it should just turn into random snow. You can't see anything. You have no idea what information. That's what you want. But electronic codebook does not do that. Large-scale patterns are preserved, and that's a serious problem. So the most popular solution for a couple of decades was this cipher block chaining, where you, in addition to the key, you add an initialization vector, which is supposed to be just a random number, and then you encrypt the first block, you XOR that with the plain text, and then encrypt it with the key, and then you take the output of this as the IV for the next one. So now each block gets an effectively random initialization vector, so even if the plain text is always the same, the initialization vector keeps changing, and you'll get random looking output. As you saw here, looks pretty good. Takes all the patterns out of it, far more than the other one. So this is fine. The problem, which I remember noticing years ago, as soon as I saw this, I said, you take the output of this block, and it affects the next block. The first thing I thought of was errors from as a child, we did woodworking. And if you would saw a board and then use that board to measure the next board, and use that board to measure the next board, you would accumulate errors until the boards are not the right size. That's one issue, but it turns out there's a related problem of padding oracles, which means this is a really bad idea. All right, so if you use the same IV every time, then the first block is always encrypted the same way, so that's a problem. So you really need to randomize your initialization vector and not use it again. Another thing about it is parallel processing. If you have a parallel processor, everybody's computers have like 4 nodes or more these days. So if you do it this way, you can have each block done by a different processor. Especially now that we have GPUs that have a vast number of independent processors, this is nice and fast and efficient. I can compute each block independently on a different processor, but this one, I can't do the second block until I've calculated the first block to get the IV, and I have to wait to do the third one until I've done the second one. This only works on a single processor. This structure means I can't benefit from parallel processing, which is a speed problem. All right. So you got 16 blocks of plain text. So I think this means if I want to encrypt plain text of hello, and I try to encrypt it, it's going to tell me no. Input strings must be a multiple of 16 in length. You can't encrypt anything that isn't fitting in a block of 16. And so you have to pad it somehow. Now, this is the standard padding technique that's been around for a long time called PKCS number 7. If you need 1 byte of padding, use 01. If you need 2 bytes, use 0202. If no bytes of padding are needed, add an entire block of 10, which is 16. That's what you do. Now, this is what's very commonly used to pad it. It turns out that combined with electronic codebook, is a disaster. And that leads to the padding oracle attack. So if you use that form of padding, and if the person who developed the system gives you a little more information, now if all they do is give you the ciphertext, then it's still secure. But if they also give you an error message telling you if the padding failed, which is, or it takes a different amount of time to report the error when the padding fails, if you can somehow tell when you feed in broken ciphertext that the decryption process failed to find a valid padding byte, then you can use that to break the system. And that's what we're going to do. And I'll do that in the projects. So that's a flaw. That's the padding oracle attack. Being able to detect padding errors make it possible to forge messages without actually knowing the key. Then there's, so a cure to this is to have a different system, a different kind of padding. What you do is you pad with zeros, but then you just swap the last 2 blocks. So you have the same thing going on here as you had before. You have an initialization vector. You take the output of this one to be the initialization vector for the last one, but then you swap the last 2 blocks of ciphertext, and you do a combination, an XOR with it here, with the padding of zeros, and discard some extra bytes at the end. So you pad it with zeros, but then you mix these 2 together in a way and swap them, and that turns out to break that problem of the padding oracle. It's considered secure, but almost nobody uses it. It's just sort of confusing to understand, it's confusing to write the code, and it turns out there's a much simpler solution. And the much simpler solution is counter mode. Remember the original one, you'd encrypt each block the same. You'd make it so one block does not depend on the previous block. Instead, you just have a counter here. So you have a nonce, you feed in a counter, and then another counter, keep adding 1 to it, or you use some kind of mathematical operation to create a predictable series of numbers, and you just use those as the IV. So you have a different IV for each one, but these can all be computed in advance, and you encrypt each block with the key and the IV coming from the counter. This is now considered the best mode. In particular, a thing called Galois counter mode is considered the best. This is what we should all be using, GCM, AES GCM, that has this Galois function that creates these counter numbers, and you use those for initialization vectors, and now you can encrypt each one of these independently. You can benefit from parallel processing, and there's no relationship between one block and the next block to exploit, so this is currently the best solution. So nonce is a number used only once, and here you take it to the first power, second, third power, and so on, or XOR it with 1, 2, and 3 is one way to do it. I think Galois uses some more complicated function than just counting up 1, 2, and 3, but it amounts to the same thing. You have to not reuse the nonce. If you were to reuse the nonce, then you'd have an identical stream of, by the way, notice something here. You take the nonce and the key, you create some random bits, and then you just XOR them with the plain text. So you don't need to pad anything here. This one is another great thing about counter mode. It's a lot like the one-time pad. The plain text is not put in until down here. So you could think of this as just a random stream of bits that you're XORing with the plain text. And that random stream of bits is like a one-time pad. What we've done here is we've made a mathematical way to create a pseudo-random series of bits from a short key that's easy to distribute. That's why I say the one-time pad is the perfect system, and AES is an imitation of the one-time pad that is almost as good. We give you a key that's short, and then you have a mathematical way of creating an endless stream of bits from that key, like the one-time pad. Then you just XOR that with your data. So as long as your scrambling routine is good enough that nobody can use that stream of bits to deduce the key, then you're in business. And that's what happens here. And you don't need to pad it. If your message doesn't fill the block, it doesn't matter, because you just XOR the bits until you're done. You don't need to have full blocks of plain text anymore, so there's no issue of padding. So that's pretty cool. You don't need padding? All right. And it's also parallelized, faster than any other mode. Although, I dare say ECB would be faster in principle, but anyway, nobody wants to use ECB because it doesn't even remove all the data from the input. All right, so that's the modes. Like I say, the bottom line is, these days we should be using AES GCM, Galois counter mode. That's the best. Those other things can be regarded as errors of the past. All right, so there's two attacks that can attack this block ciphers. Meet in the middle is why you went from des to triple des. I wondered, they have moved to des to triple des, why not double des? Why don't we just do 2 rounds of des? We encrypt with a key 1 and encrypt again with key 2. By the way they typically do it, by the way, is they encrypt with key 1, decrypt with key 2, and encrypt again with key 3. That's how they do it. And the reason they do that, by the way, is so that if you are trying to make the hardware designed for this compatible with an old single des system, you can make this perform single des by setting all 3 keys to the same. Then it will encrypt, decrypt, and encrypt again. That was a backwards compatibility function. So you could easily use hardware intended for triple des to be compatible with your old hardware that was tied on single des during the period of transition from des. Anyway, but if you had double des, key 1 and key 2, offhand, I would say now you have 2 56-bit keys. You're going to brute force attack. It'll now take 2 to the 112 calculations, which would be enough to be totally unbreakable. This should be fine. The problem is you can break it with a meet-in-the-middle attack. What you do is you input known P and you get C, but you want to find key 1 and key 2. So what you do is you make a list. You encrypt. You do encryption, you feed in some plain text that you know. You encrypt it with every possible key 1, so that gives you 2 to the 56. You have to have 2 to the 56 locations in memory you can store, which is an achievable amount of memory to get. Okay, then you take the ciphertext and decrypt with key and try all possible K2s. So you have 2 lists of 2 to the 56. Then you find where they both agree, and now you know both the keys. So you do not need to do 2 to the 112 calculations. You only need to do 2 lists of 2 to the 56 calculations, which is incredibly smaller. So you can actually get in with 2 to the 57. So double des is only 1 bit stronger than single des. That's the problem with this attack. Of course, you do need to have enough memory to remember 2 to the 56 values, but that's not an impossible number to store these days. So that's why you need triple des. If you do triple des, then you can still do a meet-in-the-middle attack. This will be 2 to the 56, but doing this one will be 2 to the 112, which is too much to store and calculate anywhere. So with triple des, you have 3 56-bit keys, and you end up with 112 bits of security. That's the idea. The problem, which is not mentioned here, but like I say, I just learned about a week ago, is that you still have a 64-bit block size, and there is an attack that came out in 2005 that breaks it just by exploiting the small block size. So triple des is now considered unsafe for that reason. All right, so then there's the padding oracle, which works like this. So you have, when you encrypt 47 bytes, you have 47 bytes of plain text, and so you need 1 padding byte at the end. So it'll add a padding byte, which is going to be 0, 1, then it encrypts it with your key, initialization vector, and each one contributes to the next one. This is how the encryption works. Now consider the decryption. You start with ciphertext, 48 bytes of ciphertext. You decrypt this one with the key, and the initialization vector XORs in here. This one, the ciphertext, which you know, XORs right here. And that ciphertext XORs here. Now consider this 1 byte at the end. If you feed it ciphertext and the ciphertext is invalid, then this byte at the end probably won't be a valid padding byte. But you do know this byte at the end has to be a 0, 1. If you fed in a 47-byte message, you know it had to pad with a 0, 1. So you know this value, part of the plain text. So what you do is you change the byte here, because this ciphertext is used as an XOR operation right here. So if you change one byte here, it will only change that one byte there. And this is why I talked about confusion and diffusion. I think this is a failure of diffusion. Let me go back and check and make sure I get that right. That was back in the earlier part. There. There. We want confusion and diffusion, which I'm not able to find here. There was a slide about that. I'm just going to search for the word confusion. There we are. Okay. What we have here is a failure of diffusion. Changing a block of plain text should change many bits in the ciphertext. They should not, remember this is on the Caesar cipher. If you change one character in the input, you only change one character in the output, and that's a pattern. And that's what we have here. That is a fatal flaw. What we have here in decryption is we can change one byte here, and it only changes one byte here. So we don't need to crack the whole thing. We're dealing with only one byte at a time. Now, when you change this, it's going to change all these 16 bytes here. It's going to change this whole block into garbage. But the next block is going to be accurate, and only one byte will change. Now, that's going to affect the padding. That is the padding bit. So, you try all 256 values here, and then one of them is going to have valid padding, and all the others are going to have invalid padding. So you can determine the one that will be valid is where you used the same original ciphertext that you knew. You know that one's valid. And if there's another one, that one is 0, 1. If that's the only one, it's also 0, 1. So when you take this value that stops giving you a padding error, you know that this is 0, 1. You know this byte from knowing the ciphertext. You know this byte is 1, so you're able to deduce this orange byte here. And you can now go back and do the byte before it. You can deduce this entire 16-bit value here. And therefore, this block of plain text is created by XORing this ciphertext with that which you have deduced. So you can now forge a message which will decrypt to any 16-byte pattern you want without knowing the key. You have discovered this intermediate value here, which is enough to let you forge part of the message. So the penalty is 16 bytes will turn into random junk, but the 16 bytes after that are under your control. That's the padding oracle attack. You're able to forge messages to give the impression that you have the key when you don't have the key, and that's a very serious failure of the encryption scheme. So that's the game. All right, and that's the padding oracle attack, and we'll do that in the projects. That's why electronic codebook is no longer recommended. Electronic codebook is not recommended because it doesn't remove patterns in the input, and cipher block chaining is not recommended because of this problem. The padding oracle means you can get in without knowing the key. So AES GCM is currently the best that does not have either of these problems. So let's try another Kahoot. This is 4B. All right. Hardware is clearly broken in there. Anyway, still works. So what system exposes AES to timing attacks? Yeah, if you're using tables, looking things up in software, that's the one that tends to have timing attacks problems. The mode of padding, which is what this is about, how you implement multiple blocks, is not relevant. It's the whether you did it in hardware or in software. All right, which system is vulnerable to the padding oracle attack? That's cipher block chaining. The part where one block affects the encryption of the next block creates a pattern you can exploit. All right, which system requires special processor instructions? That's native instructions here, built into the processor. All right. All right, which system leaves your penguin visible? Will you encrypt an image of a penguin? The encrypted version still has the penguin. This is the way people often express it because of that famous demonstration. Of course, it applies to any image with blocks of solid color. That's electronic codebook, where each block is independently encrypted with a key and no initialization vector, so any image with blocks of solid color will still show the large-scale structure in the encrypted version. All right, what system converts AES into a stream cipher effectively? That's counter mode. In counter mode, you take the key and the counter and you calculate an endless stream of bits, and then you just XOR the bits with the plain text. So it's effectively a stream cipher. It doesn't matter how long the plain text is. You don't need to pad anything. It's very much like the one-time pad. With the counter numbers and the key, you can create a pseudo-random series of bits, like a one-time pad. You then just XOR with the data. It's very nice. All right.